part of why it took so long was part of having to make that mindset change. Scientists are willing to change their minds, but reluctantly so for the most part, especially if it was your idea to begin with. And that's how science works. It's kind of the check, the balance on just willy-nilly running off to whatever's the trendy thought. So it takes time to change ideas. Well, what we had always thought of as the idea of continents in the surface of the Earth was we had these continents. They were all pretty much set up the same way. They had a core to them. In the case of the North American continent, it's the Canadian Shield, this pre-Cambrian, ancient, old rock material that makes up the core, surrounded by sedimentary rocks, mostly sandstones and limestones and shales. A lot of the material necessary to make those sedimentary rocks were simply the remnants of the shield that had been weathered and eroded and redeposited around the shield, lapping up onto the shield. So that would make that surface what kind of an unconformity? Granite underneath, sedimentary rock up above. That would be a non-conformity, wouldn't it? So sitting there means there's a big chunk of time missing. And these sediments then get re-cemented, made into new sedimentary rock. And then around these edges of these continents, we saw these mountain ranges where for some reason the edges had gotten crumpled up and mountain building episodes had occurred. But we didn't see that in the center part of the area. We saw it always kind of surrounding the edges. And every continent looked this way. Couldn't explain it to you. Couldn't figure out where the mountains came from. What were the forces? We know a lot of it's compression, but what's compressing? So there were all sorts of wild ideas out there, but none of them fully explained what was going on in any logical sense. And one of the first inklings that we got about what was causing these mountains to be there was a British survey in India. In the late 1800s, the British basically took over India, partly invited in and they took advantage and stayed. And they conquered, became the administrators of India. And as the English tend to like to do, they like to categorize things and put them into categories and pigeonhole things. And they like to know what they've got. So they immediately started surveying India. And a fellow by the name of George Everest was asked to lead a survey that would go from Kaliampur up to Carolina. So he was moving from the northern part of India even further north up to India at the Himalaya Mountains. And they were surveying it out. And this was going to be a baseline for the survey. Everything else was going to survey off this line. So this had to really be done right. It had to be accurate. And because of that, they did it 3 different ways. They used basically what we'd use laying out a subdivision today, a theodolite with a rod and a chain and, taking measurements. Now we use lasers. Back then it would have been a telescope. They also did it by just measuring with lengths of chain, set lengths of chain. And they also did it with an astronomical observatory. Big, huge, monstrous thing on a big, giant, multi-wheeled cart pulled by 8 oxen. And every day they'd pull it along with the survey. They'd have to set it up, get it perfectly level, get it all set, and then they'd be up all night shooting the stars to get their position. It's quite an operation. And they went through the survey, and I remember, this was before even handheld calculators and stuff back in the 1800s. I mean, this was all by hand. And they're out there doing this, and they finally get into Carolina, and they discover that their results between their measurements and their astronomical measurements are 150 meters off. That's like about 450 feet. And over that distance, that's not too bad, but it wasn't good. It was going to be the baseline, remember? So they went back through and they looked at every measurement. They had 5 different people keeping notebooks doing all the calculations. Every night they'd run up the calculations, make sure they all agreed. They went through all that all over again by hand. Found no mistakes. So the conclusion was, for some reason, this discrepancy in the measurement systems was real. Yeah, that wasn't what they really wanted to hear. But here's how they kind of explained it. They said, well, you know, as we started getting up toward the mountains, there's a lot more rock in the mountains, there's a lot more mass, and because of that, there's more traction, gravitational traction. So when we were setting up our equipment, we had to get it level. Well, that meant we dropped the plumb bob down, and the plumb bob would hang straight down, and we'd get directly, you know, specifically right level to right angle to that, and make sure we were dead level. And they said, well, what we think happened was, as we got closer to the Himalayas, the mountain, that extra gravity kind of pulled that plumb bob over a little bit, so when we thought it was hanging straight down, it really wasn't. And basically just didn't have the instrumentation to pull over. And that would change from being further away to just a little deviation, being closer to being a lot of deviation. So they kind of said, that's what had to happen, and they tried to kind of fix it with a few calculations and swept them under the rug. And Mount Everest got named after George Everest. Well, all well and good. But what we see is this idea now that there's a lot more mass in these mountains. Later, people that worked on the problem, J.H. Pratt, George Airy, they looked at it and they said, you know, actually, we're surprised that's all the deviation you had. It should have been about 3 times worse, which was even less than what they wanted to hear. But finally, George Airy kind of came up with the idea, and he called it isostasy. It's the same thing we see with an iceberg. For an iceberg to float, it's just frozen water. And as that water freezes, the bonds between the H2O molecules stretch out. Doesn't get much bigger, but an iceberg is typically, well, ice when it freezes is about 9% more volume than water. More volume, density is mass divided by volume. That means less density, right? So ice is less dense than water, and that means it's going to float in water. But it's going to do that only after the amount of ice has displaced an equal volume of water, or equal density of water. So you don't see much ice up top because it's almost the same density. There isn't much difference. So most of the ice is down here displacing water to make it float. But once it gets to that point, it floats. It's like buoyancy with a ship, right? Same kind of thing. Oops, let's go back. You've got the steel-hulled ship. Well, the only reason it floats is because, you know, if you threw a piece of steel in the water, you go right to the bottom one day. But with the hull, it's all that air in the volume inside the steel hull that when you calculate that in, that doesn't weigh a whole lot. It offsets the weight of the steel. So taken together, you can put a steel hulled vessel in the water. It's going to sink into the water until it displaces an equal weight of water. That's it. It's going to float there. If I put cargo into the ship, what's going to happen? The ship's going to sink deeper, displacing an equal amount of water, equal weight of water. Take that cargo out, up it comes. So it's going to be this equilibrium, always displacing the amount of weight that you've got in the system. Same thing with an iceberg, same thing with mountains. This mountain is going to be lighter density material than the underlying mantle material. That's going to be denser. So this overlying crust now is going to be floating, literally floating on this partially molten underlying mantle material, this asthenosphere. So this is partially molten. I mean, it's like maybe 2% molten. It's not liquid. It's not runny, juicy stuff. It's more like kind of a plastic, like silicone. But you probably all played the silly putty as kids. You warm it up a little bit and you let it just sit there and it just kind of oozes out, right? You put a little weight on it and it oozes out even more. So that's what's going to happen. I'm going to take this lighter crust, I'm going to put it on there, and as I start piling this lighter crust in one part, it's going to start to not only get higher, but it's also going to start to get lower. It's going to start to sink into the denser underlying material and displace it. Just like a ship displaces water to float, just like the iceberg displaces water to float, this lighter crust material is going to displace the denser material under it to create a root to this mountain to essentially float the mountain. Even though it's rock, it's doing the same thing. If I weather and erode that mountaintop and that material is removed as the streams carry it off the mountain down into the valley, well, I've got less material here to support. I'm going to see the root kind of come up, just like the ship coming up out of the water as I take the cargo off of it. And where I redeposit that sediment down here in the valley, that load is going to have to be compensated for, and we're going to start to develop a little bit of a root there to help support that additional weight there. So it's always seeking equilibrium as I load and unload this crust. It's always going to be developing a root and losing a root underneath to keep everything in equilibrium. So isostasy is just kind of the rock name for buoyancy. Same way a ship or an iceberg works. So, because of isostasy, what's going to happen here? I'm going to give you 30 seconds on this because I haven't talked about this too much yet. We've kind of done it in little scattered bits. Those clickers, they're tricky. All of the above. Well, yeah, if we think in terms of isostasy, granite is lighter than basalt. So granite that makes up the continents is going to float higher than basalt that makes up the ocean floors. And if we think of the fact that mountains have to have roots to help float this material, you're going to have bigger roots under the continents, less of a root or a thickness under the ocean floor. Same principle as buoyancy, so all of the above works here. Okay. Now, up until a few years ago, here was a geological problem we couldn't explain to you. Something called an ophiolite. And let me point out this person right here. You see him right there? And I use that person for scale as to how big this thing is. And you can see it kind of comes up and it's folded over and it gets kind of funky in here, kind of like it's different pillows almost with material. And it's dark brownish, blackish, brownish green. It's basalt. It's ocean floor. essentially. But here it is, making up part of a mountain on the granitic continent. Why is it there? How did this get here? And it's not just in one spot. It kind of tends to show up in big linear bands across the planet. The big question is, how does this fit in? It doesn't make sense. Oftentimes it would be explained away of, oh, these are basalts, these were old volcanoes, and that's why we have them on land. The problem is, there were no volcanoes like volcanic cones or any of the flow structures or any of the things we see associated with volcanoes. None of that existed along with these rocks. So it was really kind of a lame, we really don't know what we're talking about, but we're just going to kind of be little smoke and mirrors and hope we don't ask again. So we have this problem of ophiolites, and we couldn't explain it. We're going to come back to this. I'm going to show you how this can be explained. So this was one of our big issues with plate tectonics. Plate tectonics kind of got started, in a way, under different guys, back in the early 1900s. And it was started by this guy, and you need to remember his name. It was Alfred Lothar Wegener. W is pronounced as a V because he's German. And he was a meteorologist, and his thing was to figure out old weather by looking at the rocks. What was the weather like back then? Now right away you're going to kind of say, how the heck can you do that? I mean, the weather's here today, it's gone tomorrow, and if I didn't write it down as to whether it rained or not today, I wouldn't know that 20 years from now, would I? So how is he studying weather that happened millions of years ago? Well, again, it's kind of that backdoor thing. Look at how rocks are laid down today. If I go down to, say, Florida or the Bahamas, what kind of rocks are prevalent down there? Limestones, right? Carbonates. Things like coral reefs, shells, things made out of calcium carbonate. Calcium carbonate's kind of interesting stuff. Now, if I took a cube of sugar and I put it in a cup of hot tea, what would happen to the sugar? It's going to dissolve, right? It's going to go into solution. The sugar is going to just kind of fall apart, and the sugar ions that make up sugar are just going to float around in the solution. That happened because I increased the temperature, it got warmer. But what happens with calcium carbonate is if you make things warmer, it does just the opposite. It comes out of solution. It precipitates, and if I had very calcium-rich water, calcium carbonate-rich water, and I warmed it up, I'd end up with a white crust around the edge because the calcium carbonate would come out of solution and precipitate. Where is it nice and warm? Florida, the Bahamas. And what kind of rock do I have there? Calcium carbonate, limestones, right? So it all fits. What kind of rocks do we have around here? Now, we do have limestones here, but these are limestones from the ancient past, laid down when we were near the equator, when we were behaving like Florida behaves today. But what are the rocks that we get today? Think in terms of the glaciers of the last few thousand years. We've got sandstones, gravels, things that you'll come to love as conglomerates and breccias. It's basically gravel. But it's all made out of silica material, not carbonate material. And if I go even further north, up say to Hudson's Bay in northern Canada, what's going on up there? I'm not getting a lot of sediment up there, am I? Most of it's frozen up most of the time. And when I do get stuff, it's usually big blocks of stuff that kind of break up out of bedrock. So I can look at different kinds of rock type from the equator up to about 30-degree parallel, as carbonates, from the 30 to the 60 kind of as about silica sandstone.